We're going to do a little review on the acids and bases. It's chapter 14 and 15. We had two review documents. I've spliced them into one, so I won't have to switch later. We'll cover about 20. I've highlighted 20 for chapter 14 and 12 for chapter 15. And number one simply wants us to identify the conjugate acid-base pair. Remember the rules that are required for a conjugate acid-base. If you have I'm going to use the simplified version. If you have the acid and it ionizes, this part of the molecule has to be the same on that side. This is the acid. This is the base, conjugate base. And you can only have one proton missing. So if we had two here, then one of them would have to stay with that group. So which one matches? Well, we got to find one that has, first of all, that has the same A part of the molecule. OCl minus and HCl doesn't work. H2SO4 and SO4 2 minus is close, but it's missing two hydrogens. Can't do that. We have to miss just one. So B doesn't work either. NH4 plus, and then NH3, that works. We lost one hydrogen, and we've still got the NH3 part of the molecule left over. It's kind of a tricky question. Hydronium dihydroxyl is a 2-proton movement, so that one doesn't work either. So that's why the answer is C for this one. Some fresh cloth. There we go. Number 2. Hydrogen sulfate or bisulfate ion, HSO4 minus, which is one of the polyatomics that we covered in, I guess it was first semester, can act as either an acid or a base in water solution. In which of the following equations does HSO4 minus act as an acid? Okay. Let's see. They're given the proper equation. So we have to have this proton. If this is going to act as an acid, it has to oh, mine's gone blank. It has to supply the hydrogen. Donate the hydrogen. So that means this would be the base. And then we would have SO4 2 minus plus H3O plus. So this would be the conjugate base. Let's see. HSO4 minus H2O. So it's got to be A or D. And if it's an acid, then it has to be D. All right. 3. Which of the following is the equilibrium constant expression for the dissociation of the weak acid, HOCl? This is hypochlorous acid. Let's see. Okay, so we typically express the Ks for these reactions in the simplified version. So we would leave the water out and just take the protons out one at a time separately. So that means this expression would have to have proton here OCl minus there, and the undissociated here. That should be A. Okay, we'll skip that one and skip that one. Go down to 6. A solution in which the pOH is 12.1 would be described as acidic or basic or neutral. So if the pOH equals 12.1, I don't think in terms of pOH, I think in terms of pH. Right. So I would say the pH then would be equal to 1.9. Yeah, 1.9, 14 minus 12.1. So that would be a strongly acidic solution. Very acidic. Okay, 7. Which of the following indicates the most basic solution? All right, so looks like we're going to have to take a look at each one. At least 2 of the solutions are equally basic. 2 above. Equal. Okay, A is hydrogen ions are 1 times 10 to the minus 10 molar, which would be a pH of 10, right? pOH, if pOH equals 6.7, then pH, we're trying to compare apples over here. This is oranges and pomegranates and grapefruit on this side. We want to put everything into apples. So this would be 6.7 from 14 would be, and then 6 and 13, 7, 7.3. And then hydroxide concentration is 7 times 10 to the minus 5. All right, pOH, then will be the negative log of that value. Calculator. Let's see, 7, 5, and we do the log, change the sign. So that's 4 point, let's see. Yeah, 1 significant figure. I'm going to keep 2 so I can say 4.2. So pH then would be 9.8. Okay. And then D, pH is 4.2. Okay. So go back to the question. Which of the following indicates the most basic solution? The most basic is this one right here. Okay. We don't have 2 that are the same. Are we good? Okay. All right. Let's see. That was 7, 8. Which of the following solutions contains the strongest acid? Okay. Let's look at each one of them. They've each got hydrogens to dissociate. That's good. Okay, then we look at the Ks, and all of them but B has only 1 K. That means it has 1 hydrogen, so it only has 1 Ka. B has two Kas, but which one controls the pH? The first one, right? Because Ka1 is 10 to the minus 5 and Ka2 is 10 to the minus 12. So the first one controls the pH. So we don't have to consider the second one. We just look at the strongest acid would be the one with the largest Ka. And we're talking about this in terms of chemistry. Strongest acid, the concentration doesn't matter. When we say strongest, we're talking about which one dissociates the most easily. So I look at the powers of 10 first. And then if we have two of them with the same coefficient, then we break the tie there. With a different coefficient, we break the tie. The one that with the largest power of 10 is E, hydrofluoric acid. That would be the strongest acid. Okay. Now I stuck this one in there, strongest conjugate base. Which one would be the strongest conjugate base? Would be the weakest acid, wouldn't it? Okay. And the weakest acid giving you the strongest conjugate base, then we would go to that Ka2. Because it's 10 to the minus 12 would make it a very weak acid. And it would produce, I'm not sure what that is. I can't tell from the formula. But the strongest conjugate base will be produced by B. Just as a talking point. I mean, that doesn't answer the question. Right. Number 9. Which of the following statements are true? Statements are true. Okay. So D says at least 2 of the statements are true. All the statements are false is E. So let's just keep things in order here. E says all false. And D says 2 true. Okay. Then A is pH of a strong acid is always lower than the pH of a weak acid. Is that true? Now we're introducing the concept pH is dependent upon concentration. Right? So we're not just talking about the strength of the acid, we're talking about how concentrated it is. And the pH of a strong acid is not always lower than the pH of a weak acid. If the weak acid has a high enough concentration, its pH could be lower than that of the strong acid. Okay, so this one's false. pH of a solution can never be negative. Is that true? I think I showed you one in class. pH is just it's a mathematical transform. Right? So if we have a value here that say, I don't know, 10 to the first power, right? 10 molar. Then that would be the log of 10 to the first power would be 1, and that would be pH minus 1. Right? So if we're trying to say the pH of a solution can never be negative, that's false. We just showed one. That's one of those logic problems where a statement that says never or always, all you have to do is just find one exception. And that kills the argument. Then C would be for a conjugate acid-base pair, Ka equals 1 over Kb. Is that true? No, it's Kw over Kb. Remember that? Right, so that was false also. So all of them are false. Okay. Trying to be sneaky. Okay, how about number 11? For the stepwise dissociation of aqueous H3PO4, which of the following is not a conjugate acid-base pair? All right, so I'm just going to put the acid-base pairs up here based upon our rules. So the first acid-base pair would be H2PO4 minus. The second one would put this one over here, HPO4, H2PO4 minus. Get rid of one more proton, and that would leave an extra negative behind. So this one would be HPO4 2 minus. And then the last one would be HPO4 2 minus, and then PO4 3 minus. So we have examples of those. Is not a conjugate acid-base pair. So the first one is this one. Yep. A is correct. How about H3PO4 and H2? Yep, B is correct. H2PO4 and HPO4 2 minus, that's correct. D, H2PO4 minus and PO4, that's false. D is false. And we threw the hydronium in there. Because in all of these, this one is still there. That one's always there. I think that was the point of putting that one in there. So D is the false one out of that group. Let's see, 12. For which of the following 0.1 molar diprotic acids would the second dissociation affect the pH significantly? Right? They're all the same concentration. We're just comparing the first and second Ks. And the last one says the second never affects the pH significantly. Never. Okay, that's one of those absolutes. All we need is one example to throw that one out. And let's see, the first one, 10 to the minus 2, 10 to the minus 7. That's 5 orders of magnitude difference. So the second one will not significantly affect the first one. 5 orders of magnitude is 10,000 times. Okay. The second one is 0.4 minus 8. I mean, minus 4 and minus 8. That's 4 orders of magnitude, right? We still don't have an effect. Minus 4 and minus 9. That's another 5 orders of magnitude. Second one still doesn't affect. So that one doesn't affect, that one doesn't affect, that one doesn't affect. How about D? 10 to the minus 3, 10 to the minus 4, but look at the coefficients. 1.8 times 10 to the minus 3. Let's make the coefficient, the powers of 10 equal. So what would that do to 9.3 10 to the minus 4? If we brought 10 to the minus 4 up 1, then that would bring 9.4 down 1. Right? So this one is only half as much as that one. That one would affect. All right. I don't know of any acid that does that, but theoretically, the second one would have an impact on the pH because they're so close together. That's why D is the answer. All right, skip a few down to number 16. Which of the following would give the highest pH when dissolved in water to form a 0.1 molar solution? The highest pH. Okay. A, B, C, D, E. Well, A and B are both acids, right? So they're probably not going to give us the high pH we want. They're going to be a low pH. So I'm going to say let's cross those out. We may have to come back to them, but I don't think they're going to work. Potassium salt of a weak acid. So there's potassium and there's our acid. Or the potassium salt of a strong acid. Let's see, that's 1 and 2. This is a weak acid source right here. This is a strong acid source right here. Okay. And the ammonium salt of a strong acid of A, and this is from a strong acid. All right, when they dissociate in solution, you're going to get K plus and A1 minus. Okay? If this is from a weak acid, it doesn't want to be that way. Right? It would rather have a hydrogen. So this is going to snatch hydrogens from somewhere, and it's going to take them from water. Right? And that would produce this weak acid. Right? It really wants to be that way. And OH minus. Right? So I think this one would probably work the best. Okay. Sources from strong acids are typically going to give you lower pHs. Actually, it's going to be neutral, right? Potassium hydroxide would have been the source for this one and this one. But remember, strong acid, strong base combination to make a salt is a neutral solution. So this one is going to be neutral. This one, it's probably going to be intermediate between this one and that one, because ammonia is a weak base, and this is a strong acid. So weak base and strong acid is going to make an acidic solution. It's more likely going to be acidic. I was just using the rule of thumb there. All right, 19. Solid ammonium acetate. Okay. Wait a minute. There must be something above it. Yeah. Select the answer that best describes an aqueous solution made from each of the following. All right. Solid ammonium acetate. I just put the charges in there to show you they're balanced. If we didn't go into a lot of detail with this one. As I recall in the lecture, I just had this table that showed what would happen with strong acid, weak base, and strong acid, strong base, and those. And when you get to the case where you've got weak and weak, like weak base and weak acid, to form the salt, you have to compare the Ka of the acid with the Kb. Excuse me. Yeah, this would be the acid form. The Ka for the acid form and the Kb for the base form. And whichever one is larger wins. Right? So if this has a larger Kb, right, we know how to calculate Kbs, but in this problem, they're given to you. So the Kb here is 5.6 times 10 to the minus 10, and the Ka is 5.6 times 10 to the minus 10. So a 0.1 molar solution there, well, it doesn't say, it just says put them together. This is going to be pH 7, because the Ka is equal to Kb. Okay? All right, number 20. Solid ammonium perchlorate. Ammonium perchlorate. ClO4. So for the ammonium ion, we have a Ka of 5.6 10 to the minus 10. We had one earlier. 5.6 times 10 to the minus 10. This is the Ka for ammonium. And Kb for the perchlorate is 10 to the minus 21. Kb for the perchlorate is about 10 to the minus 21. Now, the reason we say that is because HClO4 is a very, very strong acid. So we estimating the Kb for this is kind of problematic because the Ka for that is essentially infinity. That's why they gave you the value instead of trying to calculate it. But if we compare these two, this one is larger than that one, right? So the solution should be acidic, right? Because the acid Ka is larger than the base Kb. And that's the quantitative way to assess it. But we actually don't need these because we know that was the parent for this one is a strong acid, and the parent for this one is a weak base. So a weak base and strong acid gives you an acidic solution. Either way, rule of thumb or actual numbers, you get the same answer. 22. Okay, which factor listed below is most important in determining the strength of an oxyacid? The oxyacid is something that has oxygens, and it could be any number. And then there's something out here. Very often what you have out here is halogens. And then you have one or more hydrogens here. Let's see. Say why. That's an oxyacid. And it dissociates one hydrogen at a time like any other acid. But what determines the strength of this acid? It's the number of oxygens. The more oxygens you have, the stronger the acid. And we can illustrate that with this homologous sequence. This is the weakest acid, and the strength of the acids increases that direction. So the answer is D, number of oxygen atoms in the molecule. The reason for that is oxygen is a very electronegative atom. It draws electron density away from the rest of the molecule. Okay. And especially if this is a halogen, the halogen's also going to draw electron density away. But as you increase the number of oxygens, you get a more a higher composite electronegativity. It weakens the bond between the hydrogen and one of the oxygens that it's connected to. And the weaker bond means stronger acid. All right, 24. Which of the species below, when dissolved in water, will not produce a basic solution? All right. A, B, C, D, and E. None of these. Okay. All right, so we have barium hydroxide. I'm going to start from the bottom. That's definitely basic. BaO. What happens to that when you put it in water? Well, it removes a hydrogen from the water molecule. This is 2 plus, and that oxygen combines with water and produces 2 hydroxyls. So that's basic. Okay. KCl. What does it do in water? Well, strong base, strong acid is a neutral. Okay. Which of the following below will not produce a basic solution? Well, that won't produce a basic solution for sure. But how about this one? There's the bad wording in that problem, because we found one that doesn't produce a basic solution. But also this one in aqueous solution yields acidic solution. It should be reworded to say which one produces an acidic solution. Right. So if this one slips by and ends up on this type ends up on an exam, then you could say either one and argue your case and get the points. But the best answer is A. Oh, wait a minute. I was looking at the wrong one, wasn't I? Yeah, my eyes flipped up to 23, and you guys let me get away with it. Right. This one, plus water, right, will produce 4 plus OH minus. That's basic. And basic. Okay, so the problem, that question's okay. It was just your instructor's mistake. All right. 25, let's see. No special instructions. They stand alone, 25. Okay. Which of the following species cannot act as a Lewis base? Okay. Lewis base does what? Well, if an acid donates a proton, it accepts an electron pair. Right? So an electron pair acceptor is an acid, a Lewis acid. A Lewis base accepts a proton and donates an electron pair. Right? So a Lowry-Bronsted acid, wait a minute, a Lowry-Bronsted base is also a Lewis base, but for different reasons. Right? So if a base can accept a proton, it donates an electron pair. That's an electron pair donate. Okay, let's see which one of these works. Which of the following cannot act as a Lewis base? So which one cannot donate an electron pair? Well, C, D, and E. Let's see what we got here. That one's got plenty of electrons, doesn't it? It can donate electrons. Right? So that one's good. How about the next one? OH minus. Yep. It can donate electrons. How about C? CH4. Right? Has it got any electrons it can donate? Nope. No, they're all used up in the bonds. So that one can't act as a Lewis base. And then H2S, It's kind of like H2O. S, like that, like that. So it's got those free electrons it can donate. And NH3, right, like that, like that, has a free electron pair. So that can act as Lewis base also. Okay? That's the one that doesn't act as a base. Let's see. I'm going to leave that up there. Let's go to 26. Which of the following species cannot act as a Lewis base? Again, 26. Okay. Let's see. N3 minus, that's got a special name. Azide ion. Right. These all have electrons they can donate. Right. We did this one already. How about this one? H4 plus. Nope. There are no electrons to donate from this one. Right, they're all used up. Kind of like methane. Okay, how about 27? Oh, which cannot act as a Lewis acid. So 26 is going to be electron pair acceptor. Which one cannot accept electrons? Well, let's see. Potassium, magnesium. Right? Those can accept electrons. Aluminum, right? That was one of the examples in our textbook, I think. H plus and H minus. So that these can accept electrons, that one can't. Hydrogen's got all the electrons it can handle. Let's see. Number 30. Let's see. Given the following values of pKa, determine which is the weakest base of the answers listed. Okay. So we've got these acids listed with their pKa's, and we want to find the weakest base. So we're looking for the strongest acid. We would produce those anions that would be the weakest base. Now here's the trick. There's one in there that's not listed in that group. Right? See that one? E. Right? That one is a very, very strong acid. It would produce an exceedingly weak base. So while we waste our time looking at the pKa's to find the strongest acid, which in this case would be chlorous acid, HClO2, right? We should have been looking at the answers to see this one down there. That's the answer. Now, if that's missing, all right, if there's something else in there, then we would go to that list and say, all right, which one is the strongest acid, gives you the weakest base. Let's skip a few repetitives. How about 38? Carbonic acid is a diprotic acid. Yep. H2CO3. That's what you get in POP. When you force carbon dioxide into water under pressure, it produces carbonic acid. In this case, the first K is 4.2 times 10 to the minus 7. PK, excuse me, PK1. And PK2 then would be larger, 4.8 times 10 to the minus 11. A 4 orders of magnitude difference. The ion product for water is 1 times 10 to the minus 14. So for water, PW, no, PKW is 1 times 10 to the minus 14. Okay. What's the hydroxide ion concentration of a solution of 0.18 molar sodium carbonate? Sodium carbonate, and we're saying it's a concentration of 0.18 molar. All right, when this dissolves, what's going to be in solution? Right, it's completely soluble. So it's going to produce sodium ions, carbonate ions, and of course you got water, are the dominant species. So which one controls the pH? The one with the largest pK. This one. So that one is H2CO3. I'm going to use the simplified version. H plus and HCO3 minus. Okay. All right. But this one is related to that one. And it's essentially going to produce, this is going to be all this 0.18 molar, 0.18 molar is going to be the carbonate. And that carbonate is going to essentially go all the way to bicarbonate. Right? So we're going to start off with 0.18 molar here. All right, how did it get there? Well, I might be barking up the wrong tree. All right. We do want to say, yeah, I gave myself a hint just to keep me from going off track. So what's the KB1? The K, this is going to be, wait a minute. That's not PK. It's just K1. KA1. A2. There we go. Okay. So what would be the KB? And what would it mean, actually? KB2. I'll leave that there. For these. All right, remember, KB is equal to KW divided by KA. Right? So all you have to do is divide this into that value, and that'll give us the KB. And 4.2 exponent 7 divide. So this one is 2.4 times 10 to the minus 8. And this one would be Divide that into it. 8. This one would be 2.1 times 10 to the minus 4. So this one controls, this one controls the pH. So what we need is not that reaction. What we need is this reaction, the second one. So HCO3 minus and H plus CO2, CO3, 2 minus. So CO3, 2 minus is 0.18, right? Initially. That's 0. Well, this is 0 also. So what's going to happen? Reaction is going to move this way, right? So the change is going to be, we're going to lose some of this. We're going to, how do we lose some of that? I'm going to have to rewrite it. Sorry. HCO3 minus and water. Like that. Then we're going to have to lose, that's 0. That doesn't count. And this is 0. So the change then would be, we're going to lose some of that. We're going to lose some of this. We're going to add this. So at equilibrium, this is X. This is minus X. And this is 0.18 minus X. Okay. What we need to do is find out what X is. Am I doing that right? Are you looking at my work problems? Oh, I got it backwards. Don't I? Because if this controls the reaction, this KB controls the reaction. I got to write it in terms of KB. CO3 2 minus and water yields HCO3 minus plus OH. There we go. That's better. Yeah, this one controls the reaction. So initially we have 0.18 here, and we have 0 there and 0 there. Then the change, we're going to lose some of this. We're going to add some of that and add some of that. And this is going to be at equilibrium 0.18 minus X. There we go. Okay, so the equilibrium expression here is going to be equal to the KB 2. So 2.1 times 10 to the minus 4. Oops, not 14, 4. And then we have HCO3 minus and OH minus over CO3 2 minus. And that's going to be X times X over 0.18 minus X. Okay. Did I assume that X was small? Yeah, because 10 to the minus 4 is a very small number. So I probably said, yeah. So this is approximately X squared over 0.18. And X then would be equal to 0.18 times that, then take the square root of it. Let's see, 0.18 and then square root. So I get 6.12 times 10 to the minus 3 molar hydroxyl. Okay. And if we're looking for what's the OH minus concentration, well, that's it. 6.1 times 10 to the minus 3. Yep. Now I danced all around that topic when I could have gone straight to the answer. Is there anybody that has trouble with what happened here today? Okay. What happens when you try to pack too much information into a small brain? Stuff starts spilling out. All right, let's look at 39. What's the pH at equivalence for the following titration? So we've got 0.1 molar HOCl, 0.1 molar HOCl, and it gives the Ka as 3.5 times 10 to the minus 8. Ka equals 3.5 times 10 to the minus 8. And we're titrating that with sodium hydroxide. Okay. So we're looking for, let's see, we're adding base and we're looking at pH. So we're going to be doing one of these things. We're looking for that point right there. Right? That's where hydrogen ions are equal to hydroxyl ions. Right? That's our pH at equivalence. So I don't dance around again. Let's look at, let's do this in two parts. We're looking at the stoichiometry first and then equilibrium. So the stoichiometry says that these are going to equal each other. Right? We're going to use up all of that. Right? So if we say initial, excuse me, let's put it in like this, HOCl. Initial is 0.100 molar. And final is 0. All right, when we do that, what are we producing? Well, we're producing OCl minus. Right, we start off with 0 there. Now we end up with 0.100 molar of OCl minus. Okay, I think that's the approach. Okay, okay. Um, yeah, okay. So it doesn't matter what the volume is. We can pick the volume we want because the volume is going to be equal in order to reach that, because you have one hydroxyl and one hydrogen and they're same concentration. So the volumes of each one is going to be equal. That's why I picked 100 milliliters. So 100 milliliters times 0.1 molar is 10 millimoles. Yeah. So times 100 milliliters. Final. This is 10 millimoles. So we have 10 millimoles here, divided by how many milliliters? Well, it's 100 milliliters from each one. So we've got 200 milliliters total volume, right? Actually, that's zero. Yeah, final is zero. Sorry. So that means we have, now we have final here is 10 millimoles divided by 200 milliliters, which is what? 1/20th, 0.05 molar. Yeah, 0.05 molar. OCl minus. Now we can do equilibrium because we've got a solution with that much OCl minus, and this is a very weak acid. So that OCl minus is going to be latching onto protons from somewhere. And it's going to have to go to water to get them. Okay, so that's what we do next. This is the concentration we start with. Now I'm wondering, OCl minus concentration is 0.05 molar. I'm wondering, can we use Henderson-Hasselbalch in this one? Could. What if we try it? We'll try Henderson. Yeah. So pH is going to be pKa plus log of base over acid. So OCl minus and HOCl. But we got to calculate the pKa. Right? We have to calculate the pKa for that. So that just means negative log of this one. There we go. I'll change the sign. 7.46. Okay. So let's see if this works. 7.46 plus log of, oh, we don't know what this is, do we? We have to find out what that one is. Did we do that calculation here? That's equal to our x. What is x? Yeah, we got to figure that out. Sorry, I was jumping the gun. Let's see. Can I do this without erasing it? If we have OCl minus plus water yields HOCl plus OH minus, then initially we have 0.05 molar, and we have 0 here, and we're going to say 0 there. And the change, we're going to lose some of this minus x, and we're going to end up with x and x. So this is x, and this is x, and this is at equilibrium 0.05 minus x. Okay, so the KB, we do have to find out KB, don't we? Yeah, we do have to do KB. So what's KB? KB is 1 times 10 to the minus 14 divided by 3.5 times 10 to the minus 8 equals. Make room there. Okay, this is 2.86 times 10 to the minus 7. Okay, so now we can say Kb of 2.86 times 10 to the minus 7 equals x squared approximately equals 0.05. I'm just going to throw the x out of that one because we already know this is a small value. And then I would say 0.05 times that value, take square root of it, and I get 1.19 times 10 to the minus 4. And that's the concentration of OH. Yeah, so we don't need Henderson-Hausbach in this case. We might as well just go ahead and calculate. If we want to know the pH, let's do the POH first. POH equals negative log of 1.19 times 10 to the minus 4. And it's already changed the sign. 3.92. And then pH is equal to 14 minus 3.92. Is 10.1. Is that the answer? Yeah. Okay. I tried so hard not to waste your time, I wasted it anyway. We just found out that Henderson-Hausbach does not help in this situation. Besides, we're still in chapter 14. We haven't introduced Henderson yet, have we? You have to know the concentrations of the acid and the conjugate base in order to use Henderson. Okay, now we're going to, let's skip through this. We're going to chapter 15. We'll finish up 15. We're doing okay. Okay. Skip down to number 4. This is chapter 15. Okay. A weak acid, hydrofluoric, is in solution with a dissolved sodium fluoride. Okay. If hydrochloric acid is added, which ion will react with the extra hydrogen ions from HCl to keep the pH from changing? Well, if it's a weak acid, right, it's going to be in equilibrium with hydrogen ions and fluoride ions. So if we add hydrogen ions, right, they're going to react with the fluoride ion. Right? That's what stabilizes the pH. Number 5. Which of the following is true for a buffered solution? What do we have when we have a buffered solution? Well, the definition of a buffer is simply resists pH change when you add either an acid or a base. Right? So the solution resists change of pH. A is correct. Solution will not change its pH very much, even if concentrated acid is added or concentrated base is added, B and C. D says any hydrogen ions will react with a conjugate base of a weak acid already in solution. That's true. They're all true. Yep. Every one of them. Okay. Number 8. How do the pHs of the buffered solutions compare? Based upon that first paragraph. Okay, you have two buffered solutions. Buffer A consists of 5 molar acetic acid and 5 molar sodium acetate. Right. So that means the ratio here, the first one, buffer 1, buffer 2. Since they're made from the same weak acid, right, acetic acid, then the ratio here is the only thing that's important. OA. Yeah, we abbreviated acetic acid as ACOH. And this is the conjugate base. And this is the unionized acid. Right? And HC. So when we mix this thing up, the first one is 5 molar, right? 5. That's equal to 1. How about the second one? This one is 0.05. 0.05. That's equal to 1 also. So based on Henderson-Hasselbalch, since they have exactly the same pKa, and they both have the log of 1, they're both going to have the same pH. The pHs of the buffered solution 1 is equal to the buffered solution 2. All right. Just for curiosity, what is the difference between these two solutions? Buffer capacity. In other words, this one will buffer at the same pH as this one, but this one will only accept a small amount of hydrogen ions or hydroxyl ions or acid and base, whereas this one will take on 100 times as much. Right, this one has a much higher buffer capacity. Number 9. Which of the following is the net ionic equation for the reaction that occurs during titration of nitric acid, potassium hydroxide? It's the same one for every acid-base reaction. That one right there. That's the net ionic equation for acid-base titration. Number 10. In the titration of a weak acid with 0.1 molar sodium hydroxide, stoichiometric point is known to occur at a pH of approximately 10. So the stoichiometric point equals 10 pH. All right, which of the following indicator acids would be the best to use to mark the endpoint of this titration? Well, the one that has a pKa close to that value of approximately 10. So who's the best candidate? Probably B. 10 to the minus 11 be the closest. Right. And the color change for an indicator, what can we see? What can we detect? Plus or minus 1. Plus or minus 1 pH. The human eye can detect. So that's within 1. Right, pKa of 11 is within 1. 13. Which of the following solutions would be described as a buffer solution? All right, in order to have a buffer solution, you need a weak acid, right? You need a weak acid and its conjugate base. And their best ratio is 1 to 1, right? Equal amounts. So let's see. Let's eliminate the ones that are not acid conjugate base. All right, first one, CH3COOH. That's acetic acid. It's just another way of writing acetic acid. All right. Acetic acid plus an acid is not going to give you a buffer solution. So A is out. How about B? Acetic acid and 0.2 molar sodium hydroxide. Barely. That could be a buffered solution because it leaves a little bit of undissociated acid behind. But it's not going to be very good, right? It would be better if it was 0.25 acetic and we neutralized only half of that, like 0.125 molar sodium hydroxide. But B will work. It's just its capacity is reduced. Sodium bromide and HBr. HBr is not a weak acid. Can't work. I'm looking to see if we've got the best answer. Ammonia and sodium hydroxide. Well, they're both bases, right? So that will work. Now, ammonia is a weak base, so it would work if we had the right concentration of acid added to it. HCl and sodium hydroxide, nope, never going to happen. So out of that, the best one is B, although it's not very good. All right. Oh, 14. Which of the following mixtures would be classified as a buffer solution? All right. So here we go again. HCl and KCl. Oh, HCl is a strong acid. It will work. B, acetic acid, 50 mils of 0.1 and 55 mils of 0.1 sodium hydroxide. You have exceeded the stoichiometric point with that much base. You've neutralized all your acid. Won't work. C, 50 milliliters, again, of 0.1 molar acetic acid and 25 milliliters of base. There, you've only neutralized half of your acid. So now you have acetic acid and acetate in roughly equal amounts. That's good. That'll give you a buffer. 0.1, let's see, D only adds 0.5 milliliters of 0.0001 sodium hydroxide. You're not in the buffer range there, nowhere near it. And E, you can't add acid to acid and get a buffer. All right. So C is your best answer. All right. Who's next? We'll skip a few and go down to 19. These indicators, with their pH ranges, right, they change color: methyl orange, methyl red, and so is alizarin yellow. Assume an indicator works best when the equivalence point of a titration comes in the middle of the indicator range. For which of the following titrations would methyl red be the best indicator? All right, this one takes some work. 19. That's why it takes 2 pages to answer that question in work problems. So we need to find out what's the pH at equivalence for each one of these. And rather than stumble around. So for A, nitric acid and KOH, those equal concentrations, when we add them together, we're going to get, let's see, for which of the following? Okay, we're going to get a pH of 7 for that one. Okay. B, let's see. I'm looking to see if it's possible to do Henderson-Hasselbalch in this one. I'm going to try it. Wait, let's do B. B has aniline with a Kb and 0.1 molar HCl. So the Ka of aniline would be 3.8 times 10 to the minus 10. This would be the pKa for aniline. That's 2.6 times 10 plus 5. What we have to do is find out what's the ratio of base to acid to base for aniline. That's not going to help us any. We do have to find out what the Ka is, because the reaction, once we get to the equivalence point for aniline, we're going to have, let's see, I think I used, yeah, we're titrating a base with an acid. Aniline is the base. We're adding the acid, and we're ending up with BH plus. So then BH plus in water is going to yield B plus H3O plus. And we're starting off with see, why did I divide by 2? Well, I divided by 2 because we have equal amounts, equal concentrations of hydrochloric and aniline. So I divided by 2 because the amount, if we have aniline at 0.1 molar, yeah, 0.1 molar, then we got to multiply it by something. So I just say 1 equals 0.1 moles. Say it's a liter. Well, we have an equal amount of the acid, so that means the initial concentration is 0.1 divided by 2 liters. Right, that's 0 and that's 0. And then the change is going to be minus X plus X plus X. So we have X here, and we have 0.100, actually 0.05. Molar minus X. And if we set that equal to our Ka, because this is acid. And the reason we did that was because at equilibrium, I mean, when we, at the equivalence point, we have added enough acid to this base, this aniline base, to make the acid. Now the equilibrium is this situation. Okay, so what's the pH at equivalence? Well, if we say this is the Ka, then this is going to be equal to x squared over 0.05. And then we'll say 0.05 times 2.63 times 10 to the minus 5, and then take square root. And this is 1.15 times 10 to the minus 3, and that's hydrogen ion concentration. So we just take the negative log of that. .94. So that's the pH for the second one. Right? And let's go back to the question. Which of the following titrations would methyl red be the best indicator? Methyl red is going to change between 4.8 and 6. So B is out. B won't work. How about C? Well, let's see. C is weak base, strong acid. Weak base, strong acid. Oh, wait a minute. C, excuse me, C. C is also weak base, strong acid. So we would end up with a similar situation here for C. Only the values, would the values be the same? 105. Okay. It would be this arrangement, right? The same concentration, because we're starting from the same concentration as before. So this is going to be x squared over 0.05 is equal to a different pKa. So the pKa for ammonia would be 10 to the minus 4 divided by 1.8, 10 to the minus 5. Hmm. 1.8. There we go. So that's the pKa for the ammonium ion. Am I losing anybody? You okay? All right. Okay, so that's 5.56 times 10 minus 10. Now just multiply that times 0.05 and take the square root of it. And that's hydrogen ion concentration is equal to 5.27 times 10 to the minus 6, and pH equals negative log. All right, 5.27. There we go. 5.27. And is that between? Yeah, that's right in the middle of methyl red. So that's a good one. I think I went ahead and did the others just for kicks. But they all came out too high. Weak acid, strong base is going to give you a pH in the range that's too high. Right. Strong base is going to give you a pH that's greater than 7. And we're looking at 4.8 to 6. So we could, actually, I didn't have to go do D and E in detail, because we could assume from the combination of weak acid to strong base that we're going to have a basic pH. that would be too high for the methyl red. Right, so we can save time with D and E. We know they're going to be basic. Let's see. Weak-based strong acid. We could have done the same thing for this one. Weak-based strong acid means this is very acidic. It's going to be much lower than 4.8. So we could have saved time on that one. If I were taking an exam, but in my mind were younger, I'd probably figure that one out. Say, by process of elimination, that's the best one. All right. What was 19? Let's go to, excuse me, 23. Okay, let's see. Do I need to go into that much detail? 50 milliliter solution of 0.035 molar hydrocyanic acid, titrated with 0.0333 molar solution of sodium hydroxide. So weak acid, strong base. At equilibrium, we would end up at the equivalence, we'd end up basic. What's the pH of the acid solution after 15 milliliters of titration has been added? Okay, so we're told that it's going to be acidic. That's because we're not adding enough base, right? Well, actually, that's misleading. It's not going to be an acidic solution, I don't think. Well, yeah, I guess it is. Okay, so we should approach this as first a stoichiometric problem, and then take the stoichiometry and go to the equilibrium. Let's see. Are we going to have enough information? No, I don't think so. Okay, we're going to have to do it the long way. All right. So, stoichiometry first. So we've got hydrocyanic acid titrated with sodium hydroxide. Hydrocyanic acid titrated with sodium hydroxide yields Cn minus plus H2O plus sodium ions. Right? Yeah. Okay, we're starting off with initial and then final. So initial hydrocyanic acid, we're starting off with 50 milliliters of 0.0350. 50 milliliters of 0.0350 molar. Right? Yeah. And we've got 15 milliliters of base. And 15 milliliters, move this down, 15 milliliters of base at 0.0333 molar, right? Yep. Okay. So finally, what we're going to end up with, and this is equal to, let's go ahead and calculate that. How many millimoles? 0.035 50 times is 1.75 millimoles. And this is equal to 0.035 23 is 0.4995 millimoles. Okay. All right, we're going to use up all of this. So final concentration here is 0. And this is going to be minus 0.4995 millimoles. This is 1.2505 millimoles of this are left. But we're going to also end up over here with a final amount equal to this. This was used up to produce that. Excuse me. CN minus. Okay, so this is going to end up with 0.4995 millimoles. All right, what's the concentration? Well, we had 50 milliliters here and 15 milliliters there. So we divide by 65 milliliters. Divide by 65 milliliters. All right. So this is going to be 1.92 times 10 to the minus 2 molar. And this is going to be 0.499. So it would be 7.685 times 10 to the minus 3 molar. You know what? I think we can use Henderson-Hasselbalch here. We just need the pKa of hydrocyanic acid equals negative log of 6.2 times 10 to the minus 10. There we go. .21. Okay, so Henderson, is that going to answer the question though? What is the pH? Okay, what is the pH? Okay, so pKa is 9.21 plus the log of the base, right, that's CN, 7.685 times 10 to the minus 3 divided by 1.92 times 10 to the minus 2. All right, so let's see. Yep, and divide. So this is 3.99 times 10 to the minus 1, and I'll take the negative log of it. I mean, the log of it, excuse me, the log. This is minus 0.399 plus 9.21. That's 8.81 pH. Is that what we got before? Yeah. No. Why is it? Okay, what happened? What did I do wrong? Okay, those values are right. pKa 9.21. All right. Am I looking at the wrong one? 23. Yeah, 23. 8.81. Now, why am I saying B? Why is the answer B there? Let me look at the question again. Titrating 50 milliliters of hydrocyanic and sodium hydroxide after 15 milliliters have been added. Well, folks, that doesn't make any sense. Because I get a pH of 8.81 after all that is. Huh. Any ideas? Why would I put 5.33 in there? Is that 14 minus 8.81? No, not exactly. That should be C. I don't understand. If I don't understand, how can I expect you guys to? All right. That's messed up. Let me see. I want to change that there. It's the pH of the solution. Should be C, shouldn't it? What do you think? Yeah. Any ideas? 8.81. I mean, that's what the calculation tells us. But the answer in here was B, 5.33. Yeah, I don't see, unless, oh, okay, here's what I think happened. This was very sneaky. The acid solution that we're adding to the base, what's the pH of that solution? Okay, I bet that's what it is. Okay, let's calculate that. Before you do the stoichiometry, what is it? Right. Before we do the stoichiometry, we've got, let's see, 1.75 millimoles in 100 milliliters. Well, there's the molarity. But, okay, here it is. HCN and H plus CN minus. And then the, that's what it is. It's not the pH of the solution. It's the pH of the acid solution before we put them together. That's what it's saying. So let's see. This is what we're starting with. 1.75 millimoles. Well, no, the pH is already given. 0.0350. That's the concentration here. This is initial change there. So this is going to be 0 and 0. We're going to lose some of this. We're going to add some of that. Add some of that. So we're going to have an X and an X, and we're going to have 0.0350 molar minus X. Let's see. Where's the Ka? Here. Ka is 10 to the minus 10, so we can throw away this X. So we're going to have 6.2 times 10 to the minus 10 equals X squared over 0.0350. Ah, a mess. 0.350. Okay, so I'm going to take, I bet that's it. 6.2 exponent 10 in 0.035 times, and then take square root of it. There. So X is equal to 4.66 times 10 to the minus 6 molar, and pH then would be the negative log of that value. Yep, there it is. Okay. Oh, that was sneaky. He didn't fool the instructor. See what happened? I worked the wrong problem. The problem was, what's the pH when you start of the acid solution? Okay. So if I get even sneakier and say, all right, what's the pH of the solution at the end of the titration, then you would do that one. Oh, you missed it. The problem that I work out here doesn't answer the question. The problem I worked out there on the board with 8.81 pH, that's the pH of the titration solution after you've added the base to it. The question was, what's the pH of the acid solution before you start? And that's what I worked out here, right? So that's the acid solution, and this is the calculation that gives you the pH. That's why it's 5.33 and not 8.81. Okay. So we've worked it both ways. So it's on record. 25. That's a case of the instructor outsmarting himself. All right, next. See how much trouble I can get into with this one. 25. All right, a certain indicator has a pKa of 9, and a color change becomes visible when 7% of it is In minus. At what pH is this color change visible? All right. I think I had an issue with the way the problem was set up originally. So when you have an indicator, remember that the indicator is a weak acid also, and it's undergoing an acid-base reaction at the same time as the main reaction. The difference is that the indicator shows a color when it changes. So this is going to be in equilibrium with hydrogen ions and conjugate base. Okay. And the color change is visible when let's see, pKa equals 9, 9. There we go, for that reaction. Color change becomes visible when 7% is in this form. Right? So if we start off with all of it here, and then change in equilibrium, then we're gonna have 7%. What's 7% of 1? 0.07, right? 0.07. So we're gonna add 0.07 over here, 0.07 here, right? So that's 0.07, 0.07. And this is going to be 1 minus, excuse me, not yet, minus 0.07. That's where I have an issue with the way I did it the first time. So this is going to be 0.93 versus those. Okay, what's the ratio then of I to, what's the pH at this change? We can use Henderson-Hasselbalch in this case. 9 plus the log of 0.07 and 0.93. Okay. So instead of saying 7% of it is in this form, that means what's left over is 0.93. All right. 0.07 there, 0.93 here. Not the log of 0.07, the log of 0.07 divided by 0.93. So that's 7. Let's take a log of it anyway. The log of that is minus 1.12. This is 7.87 pH. And we got 7.85, right? So if you do it this way, best answer is 7.85 or 7.87. That's it. That's it. Oh no, I got some more. Oh, I'm missing. Did I not? I didn't work those out, did I? Is there more to it? That's it. Okay, so I've got some problems that I didn't put in the work problems, right? Okay. Must have added these later. Let's go ahead. I probably did add these because the information that we need to discuss is important. Do it there. So we're going to look at this graph and answer these two questions. All right, so let me decrease the size of this. Won't let me. All right, so let me put the questions up here and then we'll look at the graph. 26. In the figure below, pH at first equivalence is approximately pH at first equivalence. Okay. And 27, we want to find out acid would best be used in a buffer near pH. Buffer pH. Okay, we've got, well, let's see. A, B, C, D, E. So A is 1.2, 2.3, 6.02, 9.69, and 11.85. Then this one, A, B, C, D, E. This is 1, 4, 6, 10, and 12. Okay, so let's look at this graph. First thing you'll notice is it has two equivalence points, C and E. It has two buffer ranges. Middle of the buffer range, the first buffer range is B, middle of the second buffer range is D. Right? You can see that because it goes this way once and it goes that way a second time. That means there are two hydrogens in this molecule. Right? It would be like this. And then HA minus, H plus, and A minus. Right, so you have a pK1 here and a pK2 there. All right, so the first question is at first equivalence. First equivalence is at C, right? That's 6, right there. Best buffer pH, we'll have to see what's available. The first buffer is about 2.3, right? Halfway between 2 and 3, about 2.3 or 2.2. That first buffer is 2.2 pH. Second buffer occurs at D, which is about 9.6 or 7. Right? So we don't have one in here that's close to 2, but we do have one that's close to 9.7. So that one would be the best for the second buffer. So the first one is, wait a minute, why did it say E? The pH at first hydrogen ion equivalence. At first equivalence. That's wrong. That would be at second equivalence. In the figure below, the pH at first hydrogen ion equivalence. Right, that's wrong. It should be C. There we go. Second equivalence would be, yeah, second equivalence would be 11.85. Right there. Okay. That's how you read a titration curve. I think we do that one next. Next lab exercise uses a pH meter to do a curve like that. Okay.